Good afternoon, everyone. I am Mr. Ish. Thank you for joining me. In this video, we're doing something interesting because we're looking at this concept of center of mass, or the centroid. It's an integral calculus application. The center of mass can very easily represent the central point of a region of space. Consider very quickly this. You have what I will draw over here, a parabola. Within this confines, you can see bounded by the y-axis, x-axis, and the curve. There must be a central point somewhere here which would represent the center of mass, or the centroid, and is usually abbreviated with a capital R. It's a bit of a curly R, but we're not getting too fancy here, but that's a centroid. How do you go about determining the centroid, or the center of mass of a region of space? This center of mass would have a certain x and y value. In terms of this coordinate has two values, x and y. There's a separate formula which comes into play in terms of determining the x and the y value of that center of mass. The x value comes in terms of this formula right here, 1 over a. This a represents the area of that region of space that you're looking at. If it's a simple geometric shape, you can use your basic geometry formulas. But if it's a complex curved shape, then you have to use area between curve integral calculus applications. You know what that would be. You would be looking at something like yt minus yb dx along the x-axis, top boundary, lower boundary, or you can do along the xr and xl, but with regards to dy in a vertical dimension, right and left boundary curves with difference. These are the formulas you can use to determine that area. Anyhow, looking at this right here, 1 over a along the x-axis, a to b, you'll have here x f of x dx. This right here can easily represent an integrating by parts scenario. Based on what you end up having, it can be an integrating by parts situation arise, and you'd have to do that. But sometimes you don't, and it's easy. The y value of this center of mass is again 1 over a, the same a, and along the same dimension, a to b in the x dimension. Here you're looking at f of x whole square over 2 dx. That right there represents the formula for determining the x value of your center of mass and the y value of center of mass. This part right over here is represented by exactly what you see over here. You can have area between curve calculations just simply to determine that area value. But remember, we're starting here with a new concept, therefore we'll start here with the easy item over here, easy question, and let that easy item be exactly what I will show you right now. We have a region of space here in the first quadrant designated exactly by these straight lines. You have your x-axis, you have this vertical line. Let this point here be 3 comma 2. Therefore this right here was 3 comma 0. This here is 0 comma 0. You have something here which is y equals 0. You have here an x equals 3, and then you have this equation which you can easily determine because you have all the coordinate pairs. It's a straight line, y equals mx plus b, but you know you can do the slope value determination and then the y-intercept and all of that. You'll have y equals 2 over 3x. Now you have everything you need to determine what is the center of mass of this region of space which is bounded by these lines. You're looking here at the same value determination. This is exactly what you're trying to determine, but we are learning how we go about doing it by means of this simple example in this video. A region of space right here bounded in terms of this triangle would have a center of mass somewhere right here, but we need to know an exact value. Let's first determine area, and the area doesn't have to be anything more than half base height. Because we have a geometric shape, we can do that. We have a base over here 3, we have a height 2. You'll have a 3 times 2 divided by 2, which is 3. I know in all instances the area is 3. Therefore I can jump right ahead to this determination of this x value, 1 over 3. From 0 up to 3, I have an x, which is the standard of this formula, and x, f of x is exactly right here, 2 over 3x dx. You know this right here is easy. There's no integration by parts because everything can combine together. You can bring this coefficient out. You'll have a 2 over 9. These x's will combine, x squared dx. You'll have a 0, 3. When you integrate this, it's easy. You have 2 over 9. You have x cubed over 3, upper limit 3, lower limit 0. But the lower limit here is meaningless. 0 is meaningless. When you do all of this, you're really having a 2 times 27 divided by 27, which is exactly what plays out. These cancel out. You end up having a value here of a 2. So in this instance, I'm getting an x value of your center mass of 2. So you're saying it's not too hard, it's relatively standard. And the reason why that is the case is because we're looking here at straight lines, so everything is playing out well. If we were looking at curved lines, then the determination of this a would be an extra step, because you'd be doing those area between curve integral calculus applications, which would add more complexity. Anyhow, let's look at this y. The y value of your center of mass is again 1 over a, which is here 1 over 3, your area. 3, I've determined the area already. This shaded region is 3. Again, along the x-axis, 0 to 3, f of x. What's my f of x is this? You're looking here at 2 over 3x whole square all over 2 dx. Now bring this 2 out and attach it with this. You're looking at 1 over 6. 0 to 3, open this up. You have 4x squared over 9 dx. Bring the 4 over 9 and attach it to 1 over 6. When you do that, the 4 and the 6 can cancel out relatively. You'll end up having here a 2 over 3 times 9, 27. And then again 0 to 3 x squared dx. I had forgotten a d over here. It should have been dx. 4x squared over 9 dx. Everything is good over here. Now we integrate this 2 over 27. We have an x cubed over 3, upper limit here 3, and the lower limit 0. The lower limit here is meaningless, and I'm having a little bit of a trouble here writing my 3's, but anyhow, you understand what I'm doing here. When I put the 3 in, I'm getting a 2 times 27 divided by 27 times 3. This 27 and this 27 will cancel out. I'll really end up just having a 2 over 3, which will tell me here for the y value of the center of mass, I have a 2 over 3. Now that we've determined this, let's bring everything into perspective. Allow me to erase that, and I'll bring everything in here into perspective for you all. When I redraw this representation here, I know I'm looking here at 3, 2, 3, 0, and then 0, 0. The center of mass is exactly 2 over 2 over 3. That's my center of mass. And you know you can abbreviate that as the capital R, the centroid. If you have 1 here, you have 2 here, you have 3 over here. You are looking here in terms of height 2, you have a 1 here and you have a 2 here. 2, 2 or 3 would be somewhere right here, and this would represent your center of mass. What it would also mean non-graphically is this. It would represent the central point of this space, which is bounded by these lines. If you were to somehow take a little top or like a little point and project this shape on that point, I'm projecting it on. This right here would be an area where you're balancing very well on this little point or this projection. Everything would be balanced. It would be a level balance, and you would find that there would be no tip or there would be no incline or decline with that balance over there. It would be a level balance, and that would represent a point where something of this nature can be balanced at that particular point. Anyhow, graphically, this right here is your centroid, and that perhaps is the most important part. Again, the center of mass or the centroid is designated as an x and y value, which you determine exactly as this: 1 over a integral a to b x f of x dx. For the x value, for the y, 1 over a integral a to b f of x whole square over 2 dx. This right here, this formula right here represents for those specific situations where you have the axis involved. You see how you have an axis involved? The situation is quite different, and we will see that in the future when everything is bounded by two curves and the axes are not involved. But here you have a specific function, and then the axis plays a role in terms of one of the boundary sides. But let's keep everything to this for now, for this video. In the future videos, we'll up the degrees in terms of difficulty, and we'll do some more center of mass calculations. And I thank you for watching this video. Have a good day.